Okay, so I told a couple students I was going to put together a video on how to balance redox reactions, and here we go. So one of the things to keep in mind is that there are two different ways of writing out or balancing a redox reaction. One is if the solution is, or the reaction is occurring in acidic solution, and the second is if the reaction is occurring in basic solution. When you are doing your owls, make sure you pay attention to which solution it's being done in. I believe it's the first one in the series is the one that's being done in acidic, and the second one is being done in basic. Either way, the process is the exact same way for both of them, with the addition of an extra step or two when doing basic solutions. So I'm going to show you how to do balancing reactions in an acidic solution first, and then we'll do a basic solution. So there's a series of steps that you're going to do. First is to go through and identify what the half reactions are for the reaction. So in this reaction, we get the lead 2 ion reacting with the chlorate ion, producing lead 4 oxide and chloride ions. Our two half reactions would be our lead ion going to the lead oxide, and this would be the oxidation reaction because we get the lead with a 2 plus going to a lead with a 4 plus. And oxidation is the loss of electrons. When you lose electrons, your oxidation state increases. The second half reaction is going to be the chlorate ion, and the chlorine is the thing that's involved here, giving us the chloride ion. In this case, this chloride has a +5 oxidation state. That's because if oxygen has an oxidation state of 2 negative, you have 3 of them, that's a total of 6 negatives, but overall this only is a 1 negative, so the chloride or chlorine has to have a +5 or 5 plus oxidation state. Over here it has a 1 minus oxidation state. So in this process, the chlorine atom has gained a total of 6 electrons in this process. Up here, the lead has lost a total of 2 electrons in that process. And that's a little hint of what's going to come. Okay, so the first rule, or the first step after we identify what are half reactions, is to balance everything in the reaction that is not hydrogen and oxygen. And in the owls that I looked at that I'm pulling these questions from, I couldn't find any where the non-oxygen or hydrogen atoms were not balanced. Let's pretend for just an instant that this was PB3. Okay? We've got 1 lead over here, we've got 3 leads here. We would put a coefficient of 3 on that to balance that out. Now, let's go back to reality. Our reality is that our lead has 1 on each side, and the same thing with the chlorines. We have 1 of each on both sides. So the next step would be to go through and balance each side using oxygens from water. So we're going to look at and say, all right, we don't have any oxygens on this side. Over here we have 2 oxygens in this lead 4 oxide. So we're going to balance the oxygens by adding water molecules so that we get the correct number of oxygen atoms. In this case, we're going to have to add 2 water molecules to do that. So now we have 2 oxygens and 2 oxygens. In this half reaction, we don't have any oxygens on this side, but we have 3 on this side. So we're going to add 3 water molecules to the product side of that half reaction. So in both reactions, we now have the non-hydrogen and oxygen atoms balanced. We now have the oxygen atoms balanced on both sides. The next step is to balance the hydrogens, because we just added water and there's no hydrogens on either side. In fact, there's no hydrogens in this. but that's because a lot of times the very bare skeleton of the reaction, the things that are being oxidized and reduced only, are the ones that are given for the equation. Now, to balance the hydrogens, we use what we call the hydrogen ion, the H+. So on this side of the reaction, we have 4 hydrogen atoms. We will then go over here and put 4 H+. Do the same thing in this reaction. We have no hydrogens on here. We have 6 on the product side. We are going to add 6 H+. We now have all of the atoms that we need for these 2 half reactions balanced. But one of the keys and what's at the heart of a redox reaction is the fact that we've got electrons being moved from one location to another. And if you think about in your first year class, when we did chemical reactions, when we balanced them, the only thing we ever looked at were the atoms that were involved in the reaction. We never did think about how many electrons were involved. So at this next level, we're now going to focus and look at the electrons that are involved. Because redox reactions involve balancing not just the atoms but also the electrons, it's one of the reasons why some of the reactions that you balanced in your first year class were so difficult to balance. You weren't paying attention to the electrons. This is a layer of detail that, if you did know about, might have helped you balance some reactions that were a little more difficult. So, charge is key with this. The total charge of our systems can never change. So the total positive or the total negative charge always has to stay intact. So when we look at these half reactions, let's start with this one. We've got to look at what is the overall charge of our reactant side and compare that to the overall charge of our product side. Now, all of these together, this molecule is neutral, and this lead as a 2+. So as a total charge, our reactant side is a total of 2+, because we only have the one lead, and it's the only thing that has a charge on this side. When we go over to here, we're going to see that we have something similar. This is a neutral compound. We have 4 hydrogen ions that each have a plus charge, a positive 1 charge. So our total charge for this side is 4+. We have an imbalance. And as I mentioned earlier, we need to make sure that these 2 things are balanced. The charges, the total charge on both sides must be equal. And in this case, what we are going to do is then, and this is our next step, we are going to add electrons to the side that has the more positive charge total. Because by adding electrons, which are negative, that will lower that charge. So to get a 4+ down to 2, we need to add 2 electrons. Now, this kind of goes to the heart of what's going on. I said it near the beginning that the lead is going from a 2+ to a 4+, and that involves the loss of 2 electrons. Well, where are those electrons? Right here. Let's go to this half reaction. So in this half reaction, we've got a 6 positive from our hydrogens, and we got a negative from our chlorate. If we look at the total charge of this side, we are going to see that it has a 5+ charge. We've got the 6 positives and we've got the 1 negative that gives us a 5+. On this side, we have a 1 negative. This is neutral, so we have a 1 negative total. On this side, we are going to have to add 6 electrons to bring this charge of 5 plus down to the -1. And again, this goes to the heart of what our redox reactions are. This reaction, we saw that it loses 2 electrons because we've got a lead going from a 2 plus to a 4 plus. In this case, we had chlorine going from a 5 plus to a 1 negative. And that requires the gain of 6 electrons. There we go. So for this reaction to take place, for this half reaction to take place, it must have 6 electrons. Where do those electrons come from? They come from this reaction. Now, this reaction requires 6 electrons, but this half reaction is only supplying 2, which means that this reaction must occur 3 times for every 1 that this does. So this kind of leads into our next step. Our next step is to make sure that the total number of electrons in both half reactions is equal. Because again, if you go back to your first year class, never did you ever see electrons written in the reactions. They didn't show up. Even though they were present, even though reactions exchanged electrons, they didn't show up because overall the number of electrons gained and the number of electrons lost must have been equal. And we don't show those things that cancel out if they're the same on both sides. And that's the idea here. We want to make sure that the number of electrons that are represented on the reactant and product side are equal so that they end up canceling out. So this 3 then, we're going to distribute through this entire reaction and say that we're going to have 6 electrons, 12 hydrogens, 3 lead oxides, 3 leads, and 6 water. And in this reaction, we don't have to do anything. If by chance one of these had an odd number of electrons and the other had an even number of electrons, we would have had to have multiplied both of them by a value to make the electrons equal. Our last step now is to cancel those things that may be the same on both sides and bring the 2 half reactions together. Because we have equal numbers of electrons, we are going to cancel out our electrons. We never want electrons shown in an overall balanced redox reaction. We can have them in half reactions, but not the overall balanced redox reaction. We see that we have 12 hydrogens on the product side of this, and we have 6 hydrogens on the reactant side of this. Just like math, we're going to cancel out this completely. And this is going to go to 6. And we do the same thing with our waters. We've got 6 water molecules here. We have 3 here. These are going to cancel out completely, and this is going to turn into 3. Our last step now is to simply rewrite these 2 half reactions in one by just combining them together. So 3 waters plus 3 lead, 2 pluses, plus a chlorate, produces 3 lead oxides, lead 4 oxides, chloride ion and 6 hydrogen ions. And you can tell if a reaction is correctly balanced if all of the atoms are balanced and the total charge on both sides of the reaction are balanced. So if we go through and check, we can check this now. We have 6 hydrogens, and over here we have 6 hydrogens. We have 3 oxygens, plus another 3 is 6 oxygens. We have 6 oxygens. We have 3 leads, 1 chlorine, 1 chlorine. All of our atoms balance. But because this is a redox reaction, we also need to pay attention to our charge. So do the charges balance? Well, if we look at this, this has a 0 charge. This is a plus 6 total charge, and this is a minus 1. So this side total has a 5 plus. This has a 0 charge. This is a minus 1. This is a 6 plus total for a 5 plus total. This reaction is done. It's done in acidic solution. And one of the keys here, again, is to say it's acidic because we have these H pluses. If you've done your ales that dealt with acids and bases, the H plus ion or H3O, either one of those represents an acid. So this is an acidic solution. This process is different than what the ales teach you how to do. I think, me personally, that this process is a little bit easier. It's a little more straightforward. Because really, there's only one process, because in the next one you're going to see with the basic solution, it does the same thing, exact same thing, except when we get to this point, we'll take another step or two. So let's look at that reaction. Okay, so here we are with our basic solution reaction. So we're going to go through and do the same process. I'm going to go a little bit faster because the process is exactly the same. So I'm going to kind of talk as we go along. All right, half reactions, chromate, going to the chromium hydroxide. And then the other half reaction is our ammonia, giving us, I believe it's our hydrazine. Hold on, let me go look that up. Yes, hydrazine. This reaction is full of nasty stuff. Nasty, 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 nasty. Okay. Next step, balance those things that are not hydrogen and oxygen. Oh, and we've got nitrogen. Nitrogen is not balanced, so we are going to put a 2 in front of that nitrogen, this ammonia, to balance these nitrogens. And our next step then is to balance the oxygens using water. We have 4 oxygens in this side. We have 3 oxygens here. We're going to need 1 water molecule on that side. In this, there are no oxygens, so we don't need to worry about that. Next step then is to balance the hydrogens using H pluses. There are none on this side. There's 3, 4, 5 on this side. So we're going to add 5 H pluses. On this, we've got 6, and then we've got 4. We need to have 2 H pluses. Next step is to balance the charges on both sides of the reaction. So this has a total of 0, and this has a total of 3 plus 5 and a 2 negative. This has a total of 0, and this has a total of 2 plus Up here, because this is a 3+ and this is a 0, we need to get this down to 0, so we're going to add 3 electrons. Here, this is 0, this is 2+. We need to get it down to 0, or that side down to 0, so we're going to add 2 electrons. Now, quick check. I didn't mention this in the previous one. When you get to this point and you get to the electrons have to be on opposite sides of these half reactions. If you end up with electrons on the same side in both half reactions, you've done something wrong. Why? Because they have to cancel. And the only way for them to cancel is for them to be on both opposite sides. Okay, last step, or not last step, but the next step is going to be, we need to make sure that the number of electrons in both half reactions is equal. So what we're saying here is that in this half reaction, we've got to gain 3 electrons, and this reaction has got to lose 2 electrons. For them to be equal, because that's an odd number and this is an even, we're going to have to take both of them by a value to get them to be common. And in this case, we are going to multiply this by 3, and we're going to multiply this by 2. So if we distribute that through, this is going to give us 6 electrons. It's going to give us 6 H pluses. It's going to give us 3 hydrazines and 6 ammonias. Up here, we're going to have 6 electrons. We're going to have 10 hydrogens. We're going to have 2 chromates, 2 chromium hydroxides, and 2 waters. Cancel those things that are the same on both sides of the reaction, and then bring them together. So we're going to cancel out our electrons because they're equal. That's the key. We have to have those equal. Our hydrogens, we got 5 hydrogens here. We've got 6 here, so it's going to cancel out completely, and we're going to be left with 4 hydrogens. And that's it. We've canceled out everything that we can. So when we bring these two together, we're going to have 4 hydrogens. We're going to have 2 chromates. We're going to have 6 ammonias. That's going to produce then 2 chromium 3 hydroxides. Ooh, too many O's. 3 hydrazines. And 2 waters. Let's do our check to make sure that everything is good. And we see that we have a 4+ and a 4- and a 0 for a total of 0. And over here we have a total of 0. Nothing has a charge over there. So we are balanced in terms of our atoms because we got, so our charge is balanced. Let's check our atoms. We got 4 plus 18 is 22 hydrogens. So that's going to give us 6 plus 8. Oh, man, I didn't add that up right. 6 times 3 is 18. Plus 4 is 22. Then we've got 6 plus 12 is 18. Plus 4 is 22. Our hydrogens are balanced. I'm going to go out on a limb and say they all are balanced, but let's double check. 2 chromiums, 2 chromiums, 8 oxygens, 6, 7, 8 oxygens, 6 nitrogens, 6 nitrogens. We're good. Okay, so this is where this right now is balanced in acidic solution. Acidic because we got the H+. But But this question asks us to do it in a basic solution. So here's what you do. We add, if you want to call it 2 extra steps, fine, call it 2 extra steps. We add hydroxide ions to both sides of this reaction equal to the number of hydrogen atoms. So 4 hydroxides, because that's how many hydrogen ions we have, plus 4 hydroxides. The reason why we do that is it's math rules, right? If you do it to one side, you gotta do it to the other side. Now, here's why we add that many. These two together, these hydrogen and hydroxide, make water. So that's going to give us 4 waters. Now, there is no hydrogen for this to combine with over here. So the only thing left for us to do now is to recancel our water molecules, and then we're done. So if we have 2 water molecules here, and we've got 4 over there, this is going to go away completely, and this is going to change to a 2. So that our final balanced chemical reaction is going to be two water molecules, 2 chromates, 6 ammonias. It's going to give us 2 chromium, 3 hydroxides, 3 hydrazines, and 4 hydroxides. And this, the hydroxide ion, is what makes the solution basic. And if we go through and double check, just double check again to make sure that we've got the correct number of atoms and the charges balance out. Over here, if we look at charges, we got a total of 2 negative. No, 4 negative, sorry, 4 negative. And we got 4 negative from the hydroxides. Okay, charges balance. 4 hydrogens plus another 18 is 22. 6 plus 8, wait a minute, 6, 12 plus 6 is 18 plus another 4, 22. We've got 2, this is 8, 10 oxygens. We've got 6, 7, 8, 9, 10 oxygens, 2 chromiums, 2 chromiums, 6 nitrogens, 6 nitrogens. We're done. This is our balanced reaction for this reaction in basic solution. So as you're doing others, I'm going to have a document up in Drive that has this, written out, just the steps. But you can always refer back to this video and see what all those steps are and what things to look out for. Thank you.